Hello everyone, welcome back to Applied Thermodynamics subject. Today I'm going to tell you more about refrigeration cycle, which is the chapter 3 of our subject. In this chapter, we are going to explain different concepts for refrigeration and heat pump process, which you have already seen some basic information actually in previous chapters about especially heat pumps. Also, we will discuss about various vapor compression refrigeration systems, and we will discuss about the cycle which we have in this system, and you will see also as well how one of the most important facilities in our house works. You will see basic principle of that. Before we go further, let's see a video as an introduction for today's session.
Before refrigeration, keeping food fresh was a pretty tough job. In those days, people used to salt their food or bury it in the snow to keep it fresh. But now, the refrigerator has changed the way we conduct our daily lives, making it easier to preserve food. Have you ever wondered how a refrigerator keeps your food fresh and provides you with a refreshingly chilled beverage on a hot day? Well, let's find out. Refrigeration is actually quite simple. To understand the principles behind it, just remember that when liquid evaporates, it absorbs heat, and when it condenses, it releases heat. A simple example is that when your hand is wet, it feels cold. This is the process of the water evaporating and cooling your hand. On a very humid, hot day, your frosty beer will have water condensing on the outside of the bottle. This warms your beer. To pull off this frosty feat, a refrigerator uses 5 major components: an expansion device, evaporator coils, a compressor, condenser coils, and a refrigerant. The refrigerant is a liquid that enters in the expansion device. As it passes through, the sudden drop in pressure makes it expand, cool, and turn into a gas. As the refrigerant flows around the evaporator coil, it absorbs and removes heat from the food inside. The compressor squeezes the refrigerant, raising its temperature and pressure. It's now a hot, high-pressured gas. The refrigerant then flows through condenser coils on the back of the fridge, radiating its heat to the atmosphere and cooling back into a liquid as it does so. The refrigerant then re-enters the expansion device, and the cycle repeats itself. So basically, heat is constantly picked up from the inside of the refrigerator and taken outside of it.
Okay, with this introduction, you can see that what we are going to talk about actually in this session. As you have seen in this video, we have refrigerators. The main aim actually to invent refrigerator is to absorb heat from different substances, especially our foods actually. Then why we need this equipment? Because as you know, the heat always go from the medium with higher temperature to the medium with lower temperature automatically. But in reverse direction, it doesn't happen at all, and we need to use energy to have a energy transfer or heat transfer in reverse direction. Then the transfer of heat from a low temperature region to a high temperature region requires some special equipment. We call this equipment or devices refrigerators, which you have already seen in previous in the video how it works actually. We will discuss more about its principle. Also, we have some other devices which we call them heat pumps, which with same principle, they also transfer heat from the low temperature region to high temperature region. But the purpose for these two different devices is different. As you can see in this figure here, we have a refrigerator. Here we have a heat pump here. In the refrigerator, the heat or the thermal energy actually is transferred from the cold refrigerated space by applying work, W net in. Then heat is transferred from cold region to a warm environment. And the purpose of the refrigerator here is to cooling down the inside of the refrigerator or the substances inside the refrigerator. How about the heat pump? Heat pump, as you can see, the direction of the heat transfer actually is same as refrigerator. Here also we are interested to transfer heat from a cold environment to a warm environment, which it can be the space inside the house. So again, we need WNets in. We need to use work to transfer heat from cold environment to warm environment, which can be a warm house actually. As you can see here, the principle is same, only the purpose is different. In refrigerator, we are going to cool down the uh, inside the refrigerator, but the heat pump, we use heat pump actually to increase temperature of the house. Heat pump is a substitution for different type of the heater, and heat pump can be used in some special cases. You can refer the video lecture in previous chapter. We have already discussed about heat pumps and why they are important, and uh, when we can substitute the heater by heat pump actually. Here we will discuss more about their working principle. And to evaluate these devices actually, refrigerator or heat pumps, we use COP or coefficient of performance for both of these devices. So COPR is coefficient of performance for refrigerator, and COP sub HP is the coefficient of performance for heat pump. In both of them, the COP actually is something similar to the thermal efficiency. If you remember, we had thermal efficiency term for different type of heat engines, but for refrigerators and heat pump, we have COP or coefficient of performance. Then, as you can see here, COP actually similar to what we had for heat engine actually is desired output divided by required input. The COP for refrigerated, to calculate COP for refrigerator actually, desired output is cooling effect. As I said, we are interested to cooling down the inside of refrigerator. And required input is WNet in, which is mentioned here, the work input. Later we will see how is this work input in the refrigerator and where this work is applied in the when this work is applied in the cycle. And COP for heat pump is desired output divided by required input again, but this time for heat pump, the desired output is heating effect. In other words, how much heat is transferred to the warmer region is our desired output divided by work input. And if you notice for our cases here, the refrigerator which we have here and heat pump which we have here, the QL is the heat which is absorbed from the cooler environment. If we imagine, if we imagine here the temperature, here is TL, here is TH, same temperature almost, and same amount of QL is absorbed from the cold environment and is delivered, and QH amount of the thermal energy is delivered to the warm environment in the for refrigerator, or delivered to the warm house in case of the heat pump. Then this COP for refrigerator will be equal to QL divided by WNet in. QL is the heat or thermal energy which is absorbed from the refrigerator space actually. And for the heat pump, the heating effect actually means QH, or the amount of heat which is transferred to the warm house divided by WNet in. So by these two equations actually we can calculate COP for refrigerator or heat pump. Why we are As I said, we are talking about these two devices in same time because the working principle is same, and only the scope of these application of these devices is different. And we have also this relationship between the COP of the heat pump and COP of refrigerator when they work between same temperature, and also when they transfer same amount of QL and QH to the warm environment and warm house. Easily we can prove this equation actually if we just substitute the amount which we have here, and if we notice that the QH actually here, in here QH is equal to QL is a plus W net in. So here in this equation, if we substitute this, we will have QL. If we substitute QH by this, we will have QL divided by W net in plus W net in divided by W net in 1. QL divided by W net in plus 1. Simply, we can find this equation. This is a relationship between COP of heat pump and COP of refrigerator. Once we have equal or similar QL and QH for the heat pump and refrigerator. And this is important to know the differences between the heat pump and refrigerator. Now, similar to what we have done for the heat engine, for refrigerator or heat pump also, we are interested to find the thermodynamic cycle. First of all, if you remember, we had CARNOT cycle as the idealized cycle for heat engines, and I told you that the most possible efficiency for a heat engine is when we have CARNOT cycle for that heat engine actually. Similarly, for the refrigerator, if you remember, we have already introduced the reverse CARNOT cycle in previous chapters, and I have discussed about the reverse CARNOT cycle. Similarly, here we can use this reverse CARNOT cycle in the refrigerator. Let's see the detail of this cycle. I think it is clear for you again. The reverse Carnot cycle is the most efficient refrigeration cycle, operating between TL and TH. TL and TH are the temperature of the cooler region. TH is temperature of the warmer region. So if you remember, the reverse Carnot cycle, the TS diagram of reverse Carnot cycle was like this. The direction is different, but from the Carnot cycle. But similarly, again, here we have two isentropic cycle. A process actually in this cycle uh, from state 2 to state 3, from state 4 to state 1, we have isentropic processes, and also we have two isothermal or constant temperature processes from state 1 to state 2 and from state 3 to state 4. This diagram actually can be also shown in an imaginary device for a refrigerator. If we imagine for a refrigerator, we have this component: evaporator, compressors, condenser, and turbine. Then this reverse Carnot cycle can be defined for this imaginary refrigerator. The purpose of this imaginary device is to transfer heat from the cold medium, which its temperature is TL, to warm medium, which its temperature is TH. QL is absorbed here in evaporator. Evaporator is equipment, also you have seen in the video, it's the equipment which evaporate actually the liquid, and during this boiling process, the heat is absorbed from the environment. The why evaporator can work actually, it is because of the refrigerant which we have, the liquid which we have inside the cycle in a refrigerator. the boiling point of that liquid is above the is actually lower than the temperature, the environmental temperature, or the temperature inside the refrigerator actually. Then with that, when low temperature, the liquid will evaporate, and due to this evaporation, the heat is absorbed from the surrounding, which is the inside the refrigerator. Then again it will go to the compressor, and then it will compress the liquid, the gas, because as you know here, evaporator will in the evaporator the liquid will transfer, will convert, and its phase change from the liquid to vapor. It will go to compressor, again the phase will change, and we will have a high pressure liquid with high temperature. After compressor, it will go to the condenser, then its high temperature actually will release to the environment or warm medium, and finally it will go to the turbine, and in the turbine it will go to the evaporator. This is just imaginary refrigerator actually. Our refrigerator doesn't have turbine. Later we will more discuss about that, but simply I can say that if we have this imaginary device, then we can have this Carnot cycle, this reverse Carnot cycle, which is start from state 1 to goes to state 2, state 3, state 4. The states are shown in these imaginary components for our refrigerator. Why this is imaginary device, and we cannot use this device actually because it is not a suitable model for refrigeration cycle, since process 2 to 3 and 4 to 1 are not practical. These two processes, 2 to 3 and 4 to 1, which are the in a reverse Carnot cycle actually, cannot be applied cannot be applied for the refrigeration cycle. Why? Because the process from state 2 to state 3, which is compression of a liquid vapor mixture here, it requires a compressor that will handle two phases. If you notice here from state 2 to state 3, which we have compressor, it is in this two-phase region. If you remember, in this under this dome, we have two-phase region. Here we have liquid plus vapor. Then a compressor which can handle two phases mixture actually. We don't have such a compressor actually to handle a mixture of gas and liquid. Moreover, the expansion of high moisture content refrigerant in a turbine, which is from state 4 to state 1, as you can see here, again, we have a mixture of gas and liquid from state 4 to state 1. So this reverse Carnot cycle, which we have here, however, it is our imaginary refrigeration cycle actually, with highest efficiency or most efficient refrigeration cycle, but it cannot be applied in real world due to these two limitations which you can see here. We don't have a compressor or a turbine which can handle two phase substance actually. Then we cannot, the reverse Carnot cycle actually is not an appropriate cycle to describe the thermodynamic cycle which we have for refrigerator. We will discuss more about the appropriate cycle in the next slide. But as an idealized cycle actually, the COP for the most efficient refrigeration cycle is the COP of the reverse Carnot cycle, and it is equal to 1 divided by TH divided by TL minus 1. TH and TL are temperature of the condenser or the temperature of the warm medium, and TL is the temperature of the cold medium. Similarly, the COP, coefficient of performance for the heat pump, is the maximum once we have the reverse Carnot cycle, and in that case COP for the heat pump also will be equal to 1 divided by 1 minus TL divided by TH, which TL and TH I already introduced to you. And as you notice here, both COPs for refrigerator or for heat pump will increase as the differences between the two temperature or TL and TH decreases. In other words, as much as the temperature of the warm medium and cool medium is lower, the coefficient of performance will be higher. And it is, I think, the common sense also will approve this, because if temperature of the cooler medium and warmer medium is not too much, the difference between them, it needs lower energy to transfer just few degrees Celsius to transfer just few amount of the thermal energy and reduce the temperature of the cooler medium. As much as TH and TL are closer, then COP will be higher for refrigerator or for heat pump. As I told you, reverse Carnot cycle is a useful cycle actually to start to discuss about the refrigeration or refrigerator system. But as we seen in previous slide, this cycle actually is not appropriate cycle to describe the refrigeration or refrigerator cycle. Then what can be the ideal cycle for these systems? The cycle which we have, or it is which is ideal for the refrigerator system actually, is vapor compression refrigeration cycle. This is an ideal model for refrigeration systems. In this system, unlike the reverse Carnot cycle, the refrigerant is vaporized completely before it is compressed, and also the turbine is replaced with a throttling device. Here is a schematic of the component which we have in this cycle actually. As you can see here in this figure actually, similar to the reverse Carnot cycle, we have an evaporator to absorb it from inside the refrigerator or from the cooler medium, and we have a condenser to release QH to the warm medium. But as you can see here, the compressor here, the compressor which we have here, just handle one phase substance actually, which is a gas. Here in the TS diagram, actually, it can be more clearly, as you can see here, from state 1 to state 2, which is the compressor. We are in the superheated region. In this region, we have only gas actually. Then this compressor is practical actually, and we can have this kind of compressor to handle this one phase substance actually, which is only gas. And also the turbine, if you remember, it has a limitation which it cannot handle two phase mixture or substance. But here we substitute it with an expansion valve, as you can see here as well. In the graph, I will discuss about that. Here in the expansion valve, it can handle two-phase substance actually. It is just a throttling device, and it will change the pressure of the refrigerant, and due to the change in the pressure of the refrigerant, its temperature also will change. Its temperature also will go down. Now let's see in TS diagram the cycle, this vapor compression refrigeration cycle, which is important. And from now on, we will only discuss about this cycle for refrigerators. The TS diagram for this cycle is like what you can see in this figure. From state 1 to state 2, we have an isentropic process in the compressor. We have only the refrigerant here in the compressor is gas, and it's in the compressor actually its pressure, as you can see here, is increased. Only pressure, the temperature actually is changed, and also it's due to the compression, its temperature is also increased and its pressure also is increased. In state 2, we have a superheated refrigerant. Then from state 2 to state 3, we have another process which is in the condenser. During this process, the pressure remains constant, but due to this heat release to the warm environment, the temperature will reduce. And due to this reduction in the temperature, as you know, this line actually is constant pressure line. So the pressure doesn't change for the refrigerant in the condenser, only its temperature will change, and due to this change in the temperature, its phase also will change from superheated, it reached saturated gas here, then it will go to the two phase region. Finally, it in an ideal condenser actually at state 3, we will have only saturated liquid. So the refrigerant here is saturated liquid. From superheated to saturated liquid, phase change is what happened in the condenser. And QH is released to the environment. Then from state 3 to state 4, which we have an expansion valve, the temperature of the refrigerant in this due to the expansion actually will reduce. As you can see here, the temperature here T3 is higher than T4, and during this reduction of the temperature, the phase also is changed. As you can see here, a fraction of the refrigerant from saturated liquid is changed to the vapor. So state 4, which is after expansion valve, or the process in the expansion valve actually is in two-phase region. This is the main reason which we substitute the turbine with an expansion valve. And from state 4, here we have two-phase actually substance, a mixture of gas and liquid with low temperature, which is TL actually here. Then it will go to the evaporator, which is inside the refrigerator. And in the evaporator, QL is absorbed by the cold medium or the refrigerated space actually, and it will change, the phase is changed from liquid to gas, to saturated gas, which is the initial state which we had. So in ideal vapor compression refrigeration cycle, in state 1 we have a saturated gas, and in state 3 we have a saturated liquid. This is different states which an refrigerant experiences actually in an vapor compression refrigeration cycle, and we will use this cycle to describe or to model the cycle which we have in the refrigerator or heat pump. This is the most widely used cycle for refrigerators and also the heat pumps or even air conditioner systems, which is out of the scope of this chapter. In next chapter we'll discuss about them. But the cycle which we have in the refrigerator, in air conditioner, and in the heat pumps is like what you can see here. And the components also is what you can see in this figure. Then how we can find COP for this cycle? The ideal vapor compression refrigeration cycle actually involves an irreversible, the throttling in the expansion valve actually process to make it a more realistic model for the actual system. This is what I told you and what I have already shown you in previous slide actually. Then replacing the expansion valve by a turbine actually is not practical. Why? Because it will add, however, it will add some benefits instead of if we use turbine instead of expansion valve, but the cost and complexity to design a turbine actually to which can handle two-phase or mixture of the gas and liquid is not that much practical, and the cost and complexity will be much higher than the turbine, because the turbine has some benefits. It can it may improve the COP of the refrigerator, but due to this complexity and cost, it is not practical to use these use turbine instead of the expansion valve actually. Now let's see how we can calculate COP for this cycle. First of all, this is the cycle, or this is the component which we have in an ordinary household refrigerator. You can see how are the uh, condenser coils which are in the back of the refrigerator actually, which will transfer the heat from refrigerant to the warmer environment. Here you can see the evaporator coils which absorb heat from inside the refrigerator. And here is capillary tube. This is that expansion valve actually, or throttling valve, which I told you in previous slide. And also the compressor, which is usually at the bottom of the refrigerator. And you can see here the temperature of the inside and outside. If generally the temperature of the environment or the space of the kitchen is 25 degrees Celsius, temperature of the inside the refrigerator is like what you can see here, negative 18 degrees Celsius in the freezer compartment and 3 degrees Celsius in the general part of the refrigerator actually. And to find COP for a refrigerator with these components, first of all, if you notice here, all of the components which we have here are steady flow devices. Then if we write the energy balance for the cycle which we have here, we will have something like this: Q in minus Q out plus W in minus W out will be equal to HE, or the enthalpy which goes out of the cycle minus HI, or enthalpy which goes inside the cycle actually. This will be the energy balance equation for steady flow devices. Then we need to write this equation, which is based on first law of thermodynamics, for all of these components. If we write this equation for all of those components, finally we can find COP for refrigerator like this. As I discussed earlier, the COP for refrigerator is QL divided by W net. In QL is the amount of energy which is absorbed from the inside the refrigerator, desired output, if you remember. Then QL here in our cycle is H1 minus H4. How we can find this equation much easier if we draw a pH diagram actually, or pressure enthalpy diagram for our cycle. The pH or pressure enthalpy for this vapor compression refrigeration cycle is like what you can see here. From state 1 to state 2 in our compressor is like this. The pressure is increased, the enthalpy is changed. From state 2 to state 3, which we have condenser, constant pressure, just QH is released to the warmer environment. From state 3 to state 4, we have that expansion valve. Pressure is reduced in a constant enthalpy process actually. And from state 4 to state 1, which we have evaporator, and QL is absorbed from the colder environment inside the refrigerator. Then the cycle in pH diagram is like what you can see here. So if we use this diagram actually, simply we can find QL and W net in. QL here in this diagram is H1 minus H4, and W net in this cycle actually is uh, H2 minus H1. Simply, we can find COP for refrigerator. For heat pump also, we can find the COP if, but this time desired output for the heat pump is QH, which QH here is H3, H2 actually minus H3, and W net in again is H2 minus H1. So we need these enthalpies to calculate COP for refrigerator or for a heat pump. But we have a hint here for an ideal vapor compression refrigeration cycle. H1 is equal to Hg, or enthalpy of saturated gas at P1, or pressure at state 1, and H3, which is this state, is the enthalpy for the saturated liquid at P3, or pressure at state 3. This is two hints which will help us to solve different problems related to the refrigerator, and it will help us to find COP for the refrigerator or for heat pump. The cycle which I introduced you is an ideal cycle actually. We assume we don't have any heat transfer in the components or in the lines which connect each component in the refrigerator actually. But generally we don't have this kind of the equipment or component in actual world. So the actual vapor compression refrigeration cycle, which now I'm going to introduce to you, is different from the ideal vapor compression refrigeration cycle due to some reasons, which are mainly related to the irreversibilities which occurs in various components, which is due to the fluid friction, which will cause the pressure drop, and also the other irreversibility which we have is heat transfer to or from the surrounding to different components, or uh, in the lines which, or the pipes actually, which connect different components. Due to these irreversibilities, the COP of the actual vapor compression refrigeration cycle is lower than ideal vapor compression refrigeration cycle. Let's see how these irreversibilities are effective on the working of a refrigerator, or in a refrigerator cycle actually. If you notice here, instead of 4 different states, here we have added 4 more states. So here we have 8 states actually in our cycle. The components are same, but we also include the lines or the pipes which connect these different components. Why we have added them? Because generally in actual world we have heat transfer from surrounding to the refrigerant, or from refrigerant to the surrounding in the pipes. Then if we want to show this on a TS diagram, if we start from state 1, as you notice here, first of all, state 1 in the ideal cycle, ideal vapor compression refrigeration cycle, we assume it is a saturated gas, but generally it is a superheated gas actually. And we assume that from a state 1 to a state 2, we have an isentropic process. However, generally it is not like that, and we have more this process actually from state 1 to state 2 prime. Instead of an isentropic process, the entropy will change due to the fluid friction, due to the heat transfer. And also, this is from state 1 to state 2 actually. If we consider state 2 to state 3, which is this pipe actually, as you can see here, we have heat transfer, we have a pressure drop. Then from state 2 to state 3, the temperature is reduced and we have a pressure drop. Similarly, from state 4 to state 5, if you notice here, we have again a pressure drop in this line, and from state 6 to state 7 in this pipe, actually, again, we have a pressure drop. And from state 8 to state 1, which is in this pipe, again, we have a pressure drop and temperature drop, actually, here in this pipe. How about the condenser, evaporator, and compressor and expansion valve? If you notice in the expansion valve also, if we compare this with previous cycle, it is not a constant temperature process. The temperature is dropped from even from state even in the condenser, even in the evaporator, actually. So they are not constant temperature process anymore. So this cycle actually is an actual vapor compression refrigeration cycle, which this cycle actually will cause a decrease in the COP of the refrigerator. And the differences between this cycle, the actual vapor compression refrigeration cycle with the ideal one, is the non-isentropic compression, like what I shown to you here, and also the superheated vapor at evaporator exit. If you notice here, we have evaporator here. We assume in an ideal cycle it is a saturated gas, but if you notice here, it is not a saturated. It is a superheated gas in the evaporator. This is due to the heat transfer, actually. Moreover, in the actual cycle, we have a subcooled liquid at the condenser exit. If you remember, it is this state 4. If you remember, I told you that after condenser, we have saturated liquid, but it is only for ideal cycle. In actual cycle, we have a subcooled liquid at the condenser exit. And also we have pressure drops in condenser and also in the evaporator. This is what I told you, and you can see this is dash line for ideal cycle, and this line, the solid line, actually is the what we have in actual cycle. This is differences between the actual vapor compression refrigeration cycle with the ideal vapor compression refrigeration cycle. Up to here, I told you more about the components which we have in a refrigerator or even in a heat pump. But now I'm going to more discuss about the refrigerant, the liquid, the gas, or the substance which we have in a refrigerator or in the air conditioner or even in a heat pump. How we can select appropriate refrigerant and what are the most common or most popular types of the refrigerant. We have several different types of the refrigerant, which are include chlorofluorocarbons or CFCs, ammonia, hydrocarbons like propane, ethane, ethylene, and so on. Carbon dioxide, air in the in especially which is a special refrigerant in the air conditioning of the aircraft. Why we use this kind of refrigerant? This is due to the safety issues, actually, and even water, which is we use water as a refrigerant in once we have the we are a refrigerator which works above freezing point or a heat pump, actually. The gases or CFCs are the most common type of the refrigerant, which these days we are using them. We call them by R and a number: R11, R12, R22, R135, AR502 are the most common type of the refrigerant, which are in the 90% of the refrigerators which we have in the market. For the industrial and heavy commercial sectors, we use ammonia. It is toxic because of that. It is not common to be used in the household or in refrigerator which we have in our houses, actually. R11 is used in large capacity water chillers, serving as AC systems in the buildings. So R11 is used in buildings, air conditioners. R134A, however, it is actually replaced by R12, which damage the ozone layer. You know, ozone is O3, is a gas in the atmosphere which absorb the ultraviolet ray from the sun, and it protects the earth actually against the ultraviolet radiation of the sun actually. And these gases, all of these CFCs actually are effective and will destroy O3. I'm not going to go to more detail about how CFCs are destroying ozone or O3, but simply CFC will react with O3 and will convert it to O2 and O gas, and the amount of O3 in the atmosphere will reduce, and ultraviolet radiation will penetrate the atmosphere, and it will reach the surface of the earth, the humans, and also it will decrease the temperature of the earth, and it is a reason for global warming as well. And R21 is a gas, or is a refrigerant actually, which is used in window air conditioner, in the heat pumps, in air conditioner of commercial buildings. So in the large spaces, we use these gas actually, or even in industrial refrigeration systems. It is a substitution for the ammonia. R502 is a blend of R115, R22. It is the dominant refrigerant which is used in commercial refrigeration system in the supermarkets actually. You can see here we have different type of the refrigerant, which each one of them are appropriate for a specific purpose. Why we have different type of the refrigerant? Because you know their boiling point, their latent heat, which are the characteristics of this refrigerant, is different. Then their capability to absorb energy or thermal energy from the cooler environment is different, you know, for different gases. And sometimes we don't need a gas which can absorb lots of amount energy from cooler spaces. So we can substitute with another refrigerant, because as much as the refrigerator, it can works in heavier duty actually to absorb more thermal energy from the cooler environment. It means that refrigerant is more expensive. The handling of that refrigerant is more difficult, and we also need more robust equipment to use that kind of refrigerant. So based on the application, we need to select the refrigerant, which I have already introduced you here. We have different type of the refrigerant, and they are classified based on the application purpose. And as I told you, CFC is the reason why CFC are not actually appropriate gas. They can serve our purpose actually. They can be used in refrigerator without any problem, but they are effective on the uh, O3 or ozone, and we are actually, the scientists are trying to substitute the CFCs with new types of the refrigerant which are not which does not damage the ozone gas actually. Then, as I told you, to select the appropriate refrigerant, it is important to notice which temperature difference we are going to reach between the cooler medium, cooler region, and warmer region. And it will determine the type of the appropriate refrigerant. Moreover, we need to consider the space which we are going to cool down. We are going to use a refrigerant in a refrigerator in a small size. Then we can easily select the refrigerant which is appropriate for the small spaces, or we are going to use a refrigerant in a air conditioning system to cool down a house space actually. then we need to select another refrigerant. Then the space which you are going to refrigerate actually, and also the temperature difference which you are going to reach are two most important parameters to select the appropriate refrigerant. Okay, now let's see what are the heat pump, or what are the main components of the heat pump and how they work actually. As I told you, the principle and the working principle of the heat pumps actually is similar to the working principle which we have for the refrigerator. And the only difference is the purpose. Similarly, in a heat pump, we have a compressor, as you can see here. We have an expansion valve, but here instead of the evaporator and condenser, actually, we call them the coils actually, which we have an indoor coils, which we can say it is a evaporator, and we have an outdoor coil actually. As you can see here, we have again a cycle from the expansion valve to the outdoor coil, then go to the indoor coil, go to the compressor actually, then going to indoor coil, and this cycle will continue the same component, similar to the refrigerator. But here, the purpose actually is transfer the heat from the outdoor to the uh, inside the house actually, or the place which you are going to increase the temperature. It is a heating device actually. The Usually we put heat pump between the house and environment, so the energy source for this the with the medium which we absorb the energy or thermal energy from, that is outdoor air actually, which is in the winter in the lower temperature. Especially in the winter, we are interested to increase the temperature inside the house. So temperature outside the house is cooler than the inside the house. We are going to absorb the energy from that cooler environment actually. So it is air. Generally, we absorb this energy from the air. But sometimes we can absorb this energy from the earth actually, because as much as the temperature difference between the outdoor and the indoor is more different, the temperature uh, of the outside is too much low actually, the COP, or the coefficient of performance of the heat pump, will be lower. So it is better to absorb energy from the earth. We can put these coils actually inside the outdoor coil, inside the earth. We can make a hole and put these coils inside the earth actually, and it can absorb this thermal energy from the earth actually. This kind of the uh, heat pump also, it has higher efficiency, but it needs some it costs to put these facilities inside the ground and earth. So the COP will be higher when the medium which we absorb energy from that is earth, but it is more complex to install, and it will cost higher than the air based actually, the air based source of energy. It can be also water source system, which we absorb the energy from water, which can be also that water inside in the earth and in the ground, which absorb this energy from that water, which improve the COP even more. And the capacity actually of the heat pumps is mainly dependent on this outdoor coil. And this outdoor coil, because its temperature is different from the surrounding, we have usually some freezing, some ice on the coils, which is located outside of the house actually, which it will cause the reduction in the COP of the heat pump. So if we add a heater to the outdoor coil, the efficiency or the COP of the cycle even will be much higher. In a video actually we will see more details about this. And an interesting thing about the heat pump is if we use a reversing valve, then this heat pump can be used as a heater to increase the temperature of the inside the house. If we reverse direction of the refrigerant actually in this cycle, instead of the capturing the energy from the outside and transferring that to the indoor or inside the house, we can capture the energy from the inside the house and release it to the surrounding. So, by in this case, we have an air conditioner actually, or we can use this device to decrease temperature of the inside the house. Then the heat pump system actually for the areas which has uh, the temperature of the in the winter is too low, and in the warm season temperature is not that much hot, is a very good device to substitute of the air conditioner systems. In this case, a heat pump system can provide the heating requirement in the winter, in the cold season, and also it can provide the cooler or cooling requirement in the hot season.
How does a heat pump work? All air conditioning systems, including heat pumps, rely on the refrigerant's pressure-temperature relationship. When a refrigerant evaporates or boils, it absorbs heat at a very high rate, as is the case with all liquefied gases. Since refrigerant has a lower boiling point than most liquids, we can easily manipulate it so that the only heat source needed is room temperature air. We can control this boiling point by altering the pressure placed upon the liquid. Now, let's take a look at the operation of a common split-system air source heat pump. In the summer, the compressor, the heart of the heat pump, receives cool, low-pressure refrigerant vapor. It then pumps this vapor into the high-pressure side of the system. This hot, high-pressure gas now travels through a routing valve known as the reversing valve to the outside coil, which functions as the condenser. In the condenser, the heat is removed from the refrigerant by the outdoor fan, causing the refrigerant to condense into a liquid. The liquid refrigerant now bypasses the first expansion valve by means of a one-direction valve known as a check valve. The refrigerant, now cooler but still under high pressure, travels along the liquid line to the indoor unit where it is forced through the second expansion valve. This valve partially restricts the flow of refrigerant, creating the needed decrease in pressure, which allows the refrigerant to start evaporating. As the refrigerant evaporates, it absorbs heat from the passing air. In addition, the cold evaporator collects moisture, which provides dehumidification for the home. The refrigerant then travels back to the compressor, where the process is repeated over and over again. During the winter mode, the reversing valve reroutes the refrigerant path, thereby making the outside coil function as the evaporator and the indoor coil as the condenser. The heat is absorbed from the outside air by the evaporator, then brought inside and released by the condenser to heat the home's air. Also notice the outdoor expansion valve is now active as the indoor expansion valve is bypassed. This is a very efficient and cost-effective method for heating the home. There is one inherent problem, however. In order for the evaporator, now outside, to absorb heat, it must operate at temperatures lower than the outside air. This very low operating temperature allows ice or frost to accumulate on the outside of the evaporator. The remedy, the defrost cycle. As the defrost cycle is initiated, the reversing valve switches the refrigerant path back to that of the summer mode. This allows indoor heat to be transferred from the inside airstream to the outside coil, thereby melting the accumulated frost. To speed this process up, outdoor fan operation is terminated throughout the defrost cycle. Also notice that the indoor airstream, now being robbed of its heat, becomes very cold, which is not a desirable condition during winter. To compensate for this condition, the auxiliary heat is activated for the duration of the defrost cycle. After a few minutes, the outdoor coil is frost-free and the defrost cycle is terminated. And that's how a heat pump works.